Так, ну для начала всем спасибо.
Well, thank you very much for coming to hear about this topic. Well, most of the speakers have slides about themselves, but not me. My name is Timur Chernych. Now I work for Group IB. I'm a lead developer of Linux for the end users. I develop EDR agents. And today I will be talking about patching the kernel, live patching. My colleague is Yelena Bukavchenko. She helped me to prepare this, but she couldn't come today, unfortunately. So that's why I'll be the only speaker on this topic. Okay. To begin with, the overall goal is to have a kernel model to patch the system, to do it in production and in a stable fashion, and for as many operating systems and their versions as possible. Okay, this is an EDR agent. What do we need? We need to develop an event in the operating system. So I'll tell you how we're going to do it. So we need to generate the event, to collect information, to transfer it to the user space. It should be stable, it shouldn't fail, it shouldn't be very demanding of the kernel build process. We do it locally. It should load dynamically and unload dynamically. This is really important. This is important for the live updates, and it should also control the system. Well, I have 3 clarification questions to make our speech interactive. Who knows the C language? Who develops in the C language? Okay, and what about the assembler? Who knows the assembler? And who knows the in-kernel development? This is great. Okay, I'll share with you as many details as I can then. The options we've had. We have considered eBPF plus XDP and the LSM hooks. Well, eBPF is the improved packet filter, which was used for the previous operating systems to filter the network traffic, and with the extensions, XDP, which came up later, and this became a virtual machine, a full-fledged one, working at the kernel level, inside the kernel, with its pseudo language, which resembles C. And the LSM hooks are the security models of Linux, which let us have hooks catch system calls and events, brings their contacts, and it's very secure. But there are some tricks here. eBPF plus XDP is not good for us because it doesn't have enough functionality. Well, we have enough functionality, but we don't have control over the system. And, well, the kernel should be built on BPF, and we don't have a lot coded on BPF. I mean, the critical functions of the core. LSM hooks with the senior versions of Linux cannot be exported anymore. So the kernel module developers cannot do it. So if you develop the kernel, please use LSM hooks. If you don't code the kernel, please find a solution or recode it altogether. Okay, what are the options left? You can use ftrace, and you can use also key probes. Well, this doesn't really work, so we'll use patching, kernel patching. Why so? Well, it works in any case. So if you properly code, we'll be talking about it. This is 100% reliable, and it gives us control over the system. So if you heard about rootkits and how you catch control over the system and how patching happens, so the major source of information will be the system calls. And we'll start with them. And we will see the requirements we need to start patching. We need 2 configs, call sims and k probes. Call sims gives us information on the kernel symbols. Just like in any binary, you have symbols in the kernel. You need it to find the addresses, and we'll use calsims lookup name, which is not exported in the more senior versions or junior versions. And we also need to config kprobes. We need it to proceed in this process, and I'll be talking about it now. You can hardly make out the code here for kprobes, so to legitimately set the live patches. It works this way. That's an interruption with the log. Then when the interruption comes, so a handler will give us the control in our kernel module. Well, this is an interruption, and the kernel is in this environment, but it will help us find the calsims lookup name to look for the addresses of functions inside the core. How does it work? So you set the kprobe, and the structure kprobe with the hook will give us back the address of the function. So we use kprobe to find calsims lookup name, and so we use this to find the address and the attributes of the address. You can hardly make out the code, so let me explain it. Well, I have shared with you the essence of it, so let's proceed. So we are starting with the system calls and signs. Quite a lot of people know what C is, so I'm not talking about signs here or indicators. Okay, I'll ask you a question. What's wrong here? We find the system call table, and this macros nr open will determine the system call number in the table. The sysopen handler is our function in the kernel. We can do it this way, but what will go wrong in this case? Any ideas? The discussion is partly off the mic. Yeah, cache. Here is a mem for you. Okay, you understood it? Okay, the issue is in the cache of the processor. So, you know, these stones which are used to process the information are not perfect, just like the programmers. And there are mistakes there. That's why we need to optimize the code, and we need to have access to the cache processes and to hot cache process. And there are some issues. You have a lot of load, cache is very hot, data is updated there all the time. So L1 continuous reading data, L1 instructions. And we have some issues in the cache, where the processor detects that the data in the cache is not exactly right. There are a lot of conflicts, like cache misses. Let's talk about a straightforward example. The old process where the cache is not associative, the risk of mismatch is very high. What will happen then? So you can see the cache line with some data. So we have the system call, sysopen. So we are reading the table. So this is a mismatch. Okay, the address will not fit here. Okay, what will the processor do? It will read this to the end. And if we change the indicator in the system call function in the system table, this will be the result. Okay, what will happen then? This will be a page fault, and the kernel will jump to a wrong address, so we don't know where it's going to jump. So it's going to collapse, maybe not instantly, but we'll see the gradual stumbling of our machine. Okay, what to do? Oh, several options. we need to ban. Well, you know how we avoid race conditions. So we use mutexes everywhere, but we cannot use mutexes for some code we haven't authored. So we cannot use synchronization primitives or mutexes for the kernel which is compiled, which is an array. So we can mark this page with the memory as a no read, but we don't know what's going to happen. So the only solution, we believe, is to ask all the other processes to wait and do nothing. I mean, nothing at all. Okay. We have a good mechanism here, asymmetric multi-processing. So it lets us make all the processes but one do something, some kind of job, one job. Okay, we have 4 CPUs, virtual or non-virtual, so they do their job. So we have CPU 4, which wants to change the call table. It will call the SMP call for some routine. So the other 3 processes will be working there and wait for process 4 for a sign that you can proceed. The 3 processes, including this one, will switch on the preemption mechanism. So when we have 1 core but 2 virtual cores. I mean, when the tasks go through the scheduler for 1 CPU, we do this so that the 3 processes shouldn't do something apart from the waiting routine, because otherwise it will cause the CPU failure. Okay, and the 4 CPU will switch off preemption and all the interruptions, the hardware, the software ones. So we replace the addresses, say proceed. Okay, good. We have patched the system table, the system calls table. Good, good job. The code looks like that. Hopefully you can make it out. This is the waiting routine. We send the structure with a timeout. We need the timeout. I'll tell you why later. So we'll need it to offload or unload. Here we switch off all software interruptions. We have the processor ID, so that we have SMP for some other process or cores. We don't have all the processes in this routine, which will freeze the operating system. So we are there in the while loop to kind of wait until we are told to continue. Then we have the preemption and reverse interruption. So many of us are developers here. We don't like making mistakes, and we have macroses. So I would suggest enriching all that with the macroses looking like that, give or take. So this way we'll remove the memory barriers so that we have a guarantee that the whole code will be run before something goes wrong. So the trap function, so we can bring there the data and some flags, the waiting code, and so on and so forth. So we'll wait for all the processes to get out of the routine. So then we call the CPU relax so that we don't overload the processor. So we have a brief code to patch any sign, and it looks like that. So the pros and cons. Here they are. Okay, the most important negative of this approach is that the machine will not work for some time. All the things done by the stone will be re-recording some table of system calls. When it is a high-load server, this can be bad, because we have the database and we have this response per second, and so on and so forth. But the advantages are there. We don't fail. We want the kernel model to be safe. And this works for almost everything. So when we cannot launch something and use mutexes, we can use this mechanism. And this module is usually loaded before the start of the user programs. Well, this will not be seen with the cold start of the system. And the second issue, the context. So we have the patches of the system calls, and so we need to find the information on what is going on. Well, this is a very brief thing, only one mem for 16. This is the kernel version. Every signature of the syscall there is just a function with a clear call convention. In the registry, Rx will have the number of the system call, and then I can't remember the arguments exactly, how it is split, but they will have the arguments anyway. So sometimes the sign for the user space memory, and so on and so forth. This is not that important. We need to have the same function signature, and we want everything to work. Okay, and this is the kernel for 17. Okay, I'm showing this macroses. The previous one is not very informative, and here only one line is informative. Here it is. In the latest versions of the kernel, any syscall doesn't have the arguments, unlike it used to be done in the past. Well, they are transmitted, but it comes to the system call as a ptrx structure. Just imagine, we have a lot of syscalls, and we need to have this if kernel version 4.16, then this signature, otherwise that signature, and so on. So we'll get the arguments in different ways, and so I can see you're frowning, you're not happy. So this is a straightforward solution. We are using C as a language. That's why we will cover it by macroses, but only once. I'll be glad to share with you how it works. I believe you can take a picture and then see the details. It's a lot of code here, and it's not all of it. So I believe we should consider the way these macroses are going to work, so that we have this signature function once in the kernel signature, so that we don't have to think about it anymore. Okay. We are coding a macros for the signature of the function where we describe the arguments. It will be dependent on the kernel version. So there will be two signatures. One will receive ptrx, the other one will receive arguments. And we'll have similar macroses. Here it is. There we'll be sending the number of the argument and its title in the signature, function signature. This way we'll see the body of the function, how it would look natively. So here you can see the EUD sysopen, and we just equalize it. I mean, we kind of double the variable, and it will be optimized in some registry. And with the versions 14, 17 plus, we'll have everything, and we'll optimize this, so it's nothing to be afraid of. So this is a brief argument-related remark. Okay, everything is nice and fluffy. We have patched all the syscalls. So if we cannot see any process in the system, why? How come this happens? So we can see the processes, but we cannot see them in the old cores or kernels. So why so? We have tried to address the issue for quite some time, and here is why. So the previous versions 310 and some minor updates. So there we don't have a single syscall which will generate a process which wouldn't be wrapped into steps. So you can see, or stubs. So you can see the redefined from the top. So we read the source code, we see the sysclone and sysexec. Well, as a matter of fact, they are stubs. We see them in the syscall table. We can find them through the syscall lookup name, but we will find this gibberish in the syscall table. Well, nice. Okay, but if we use this stub, then the kernel will fail. Why so? Well, it's not really clear. We have figured out it for some time, and one might say that C5 is the culprit, but they are not implemented for x86 and they are not used for the Linux kernel. So that's why the major problem, calling the failure, is not known. So maybe we have some work arounds there for the stat frame, and so when you go to the process, the generated process, some frames are removed. So if the hook is added, then we have one more frame, so it is not removed completely. We have a data corruption somewhere, and it all fails. This problem has to be addressed. We need to support all the versions of kernels. Okay, what we'll do? Okay, we'll patch the instructions. Yeah, it's quite extreme doing the kernel development. Okay, how are we going to do it? Okay, well, if it's ED64, that's pretty straightforward. We look at the listing of stubs, and in the middle, we will see the jump or call instruction. For x64, we don't have an air jump or far jump, so the instructions will look the same, and this will be 5 bytes, and it's easy to find this. So before that, I talked about the call sys lookup name. So button. This way we'll find the size of the symbol. So we'll find the exact VE, the size of it, and go through this memory piece to find the instructions. Okay, we have all the data. We have the hook, the address, and we have the initial address of the initial syscall, so we know where the call is going to jump. And we know we can see the shift, say, plus bytes from the instruction. So we just recode this shift, we enumerate it, and this works. Enjoy. Okay, the most difficult thing. You remember climbing trees in your childhood. You remember that going back from the tree is the trickiest thing to do. So in all this mess we have arranged in the kernel is to fix all of that. You remember we had this requirement. So this is live patching. So we kind of replace the modules, kernel modules, as if nothing were happening. Okay, the issue. Number one, we don't know the context. So when our hook is called, it is found just like a syscall. So we don't know who called it, why they called it, when they are going to call, whether they are going to do it, and whether they have really called it. We will talk about it later. It looks like that. So this is a real frame. Okay. We call the hook, and then we call the original to maintain the kernel. Okay. The process, the syscall, the hook, we call the original goes back to us, and we return to the process. Okay, what's wrong here? What's going to happen if you want to update our kernel module to upload it? a part of the discussion is off the mic. Okay, we have called the original, the kernel module is loaded. So where will it go back? Our module is missing. So the original will go to some trash memory. It can be anything. And this is pretty bad. If you have faced issues like that, there are some obvious things to mention. So maybe we don't offload until the functions, original functions are called. So we just have the meters. The meters are there to keep track of the calls and so on. This is well, kind of easy, but there are some other issues. Any ideas? For the high-load servers, we won't be able to offload because we'll be called too often. And there are some other great, but well, things like accept and select, read, write for slow HDDs. So this is an issue. We don't know the extent to which we've been called. Okay, we have given the original function some control. When will it go back? Maybe it will go to the task wait, and then we'll be just waiting there, but we need to offload. Okay, we can wait, and the call time problem is quite easy to be quickly solved, but we can solve the problem with our continuous call. Okay, we have some ideas. Well, we can arrange it in such a way that the function we have offloaded shouldn't come to us, but it should go through us. So I don't know whether you have solved these problems. Some theory, how it works. So we have this atomic meters, and then when we are called, we send the control to the original function, but this meter is not adding up because we are not doing any job. So the function doesn't go to us, it goes back. So with the previously called function, this is not going to work, but all the new calls will be properly proxied. How? This is all coded in C, and in C we cannot do this. Okay, then we should go to the assembler and work some tricks there. Okay. Every function has a stack frame. This is a local warehouse with classes and variables. It's only for our function. So there are the scope controls. So what we need? We need only the return address at the top of the stack. So that's how they call us. And this is the callee. Okay, we take the previous stack pointer, bring it to the waste pointer, and push it to the stack. So the call just brings the return address to the stack, to the top of it, and in the base pointer. So we have this return address. So RBP is the return base pointer, and this is the foundation for our function stack. So we kind of, well, we remove this frame so that we don't have the return of the function. So that when they return the function we called, when the frame of the function is gone, the return address should go to the process which called us. Is it clear enough? Okay. Here is some illustration to help you. How we can sort it out. Okay, this is the Invoke Syscall. So it's calling us. We call something sys, so it goes back here because we destroy the stack. How do we do it? So if you don't know the assembly, I can tell you. We just push 4 bytes. This is the minimal. So here it says 8, but we can even take 8. So we remove the stack until we reach the base pointer. Okay, we find the base pointer. Okay, the frame is destroyed, so this should work, and this really works, but not always, and here is why. When we build the kernel module, we cannot always control the flags. Sometimes the compiler starts to over-optimize our code, like squeezing the variables. Sometimes they don't align them, sometimes they align it in the wrong way. We can just miss it. Okay, in AVP, we will have the frame we need, but we'll never find it with the stack. And the small routine will destroy the whole kernel, and we don't really want it. Okay, how to solve the problem? Number 1. Don't do it this way. The shorter the code, the better. So this was a kind of a workaround method. So let's remember the compiler doing it when compiling. So they use this leave instruction. Okay, let's go to the GCC documents. There we have a short routine describing the way the leave instruction works. So it's all pre-coded for us. That's nice. So we can entrust the compiler with doing it. So pros all around, and this is a working algorithm. So the second version of the frame looks like that. Okay, we call the leave instruction. We pop AVP. We update regs, and we jump to the original function, and our frame kind of disappears. Does it really work? Okay, if we wanted this, then it works. So this is kernel panic, by the way. Okay, we can see the panic. We can see the null pointer dereference. Well, it's not really that. It's kind of reading some wrong variable from somewhere. Okay, we look at the register and we see that in the AVP we have the non-canonic address. So the canonic addresses are always used by the kernel as segments of the text. No, okay, no extra detail here. So we can see that the address is wrong. It is not canonic. It doesn't belong to our frame. So why it's in RBP? Let's proceed. This is an article. Okay, shall we get discouraged? Okay, that's kind of a meme. Why does it happen? We cannot completely control the compiling flags. Sometimes the compiler overdoes it. And in some functions, we don't have the preface to keep our frame. Why? The x64 architecture, well, doesn't really need this preface. This is a kind of rudiment. Okay, we have it for the old versions of the compilers, and in the new ones, if you're going to use them, and we are most likely to do it, because we know good customers keep track of the kernel versions, we will not see any preface. And the kernel can be built by the position-independent code flags, by area 5th instruction, they will call themselves to maintain the position with the stack. But we need the preface, since all the algorithm of removing the frame is related to the fact that we want to have the address of the frame. And now we are fighting with GCC. I'd like to thank GCC for giving us weapons to fight against them. Okay, we want to leave no choice for the compiler, but to build a preface for us. Okay, when compiling, we can make the compiler calculate the address of the frame. Okay, this base pointer, the base, is not really always necessary, but when we call this, and this is done in the compilation process. So when we call this function, we force the compiler to calculate where the frame ends. And we have a kind of warning there. Well, please don't do this. But this is about our attempts to get the higher frames. But we don't need any higher frames, we need only our frame, so it is similarly secure. Okay, and this is the final version, which really works. Well, but it fails, of course, the kernel failure. Okay, the reason. Okay, why? Why another failure? Here is where we store our data. Similarly, these are some registries like R15, and we have some base registers, and we have these R registries, so they are similarly useless. But that's only on the face of it. They are really useful. We have the caller-callee safe concept, which means that some registries for the callers and callees should be stored or recovered when you go back, when you return from the function. What does it mean? We have abused these registers to save the data. Okay, we can save some other registers, which shouldn't be saved in the call. Anyway, it will be destroyed, all of it. Okay, we're not going to use them, but they'll be used by the compiler anyway. And we say, why, the compiler, are you using the registers you shouldn't be using, or you should be restoring them? But it does restore them, but it restores them at the normal return we are not using. You remember? To reduce this load on the atomic meters, we destroy the frame completely, and then we do the jump. We don't have any return. The compiler, when compiling this, just leaves the code as it is. Well, restoring these registers manually. Well, we don't know what the compiler is going to compile. What can we do about it? Those who use C for coding, what are the ideas to go around the problem? A part of the discussion is over the mic. Well, you know, in hooks we usually have a lot of things happening. Okay, we can have the stub, you can link it by C and call some other function, but this is a lot of effort. We want it to be faster and cheaper, so we're talking about business here. Okay, we wait. Okay, we will not unload from the high load servers. Microphone, please. Okay, we will not load until we have unloaded. Linux will not let us do this. Patch yourself. Well, patching yourself is a good idea until you start bringing packages which are KMS built, because you have the rotating cycles of self-patching, and the call table will be destroyed this way by this random addresses. Okay, we have a good solution from C, and it is volatile. it tells the compiler that these registers shouldn't be used, because if you use them, your hardware will be damaged. And this works. All of our hooks are in the C file. So when we have these variables, so this is not seen. So we tell the compiler that for this file you don't use these registers. Okay, this can reduce the performance, and it will give us some stability. So we can reduce performance in some small routine of the hook. Okay, this works really well. It looks like that. So all these registers are locked, and the compiler will try to do its best to go around them, because touching them is forbidden. Well, at this very point, I'm concluding, and I can tell you that this is the latest hack, which does work. Thank you for your attention, and you are welcome with your questions. Hello. Thank you. You said that you can pause all the process and change the target CPU, right? Right. Okay. Maybe you stopped it at some bad time. Maybe the CPU is kind of copying something and you want to change it. So it's on pause, you change it, and the CPU has the old information. Thank you. Well, we should clearly understand what kind of pointer we are changing. Okay. We are changing the read once syscall table. So it will be read once, and it is not likely to be reread before channeling the workflow. Okay, the pointers we patch. They're usually the structures in VSS and in networks, in the drivers, I mean, FS operations, socket operations, SKB operations, they are also read ones. So they are read ones and have no further impact. So we don't have any conflicts like that. Anything else? Thank you. You said that you want to destroy the stack frame. So you go up through the stack until you reach the address, and if you find the 8 bytes matching the address, so will you recover the registers from the previous function? You jump back, and then you have a failure. Can it happen? That's a good example, and a good question. Let me go back to this slide. Well, a similar issue might pop up here, and the same value can be here, but the solution is different. With built-in to the frame address, it shouldn't be there. But for the first version, indeed, it is not right, and it was discarded on day one. It is problematic. Thank you. Really exciting. One of the most exciting speeches, I would say. Have you tried to bring together ICC, Talang, if this patch needs a lot of performance? So in C, you cannot see this great opportunities. Thank you. Thank you for the question. This is a great question. I believe that the kernel should be rebuilt using Clang, but the longer you dig into the kernel, you start understanding it's GCC related to a large extent, and this is impossible. So when we deliver the RPN dep package or anything, when we send this package to the customer, and the package will have the dependency on the KMS, the package manager will quickly understand that we need a compiler to download, kernel develop, and GCC will be that. Okay, we can try to use klang, and we can say that this is better to optimize the code. It is not very likely to happen. Theoretically, yes, but we haven't experimented there, since we don't have any business need in it. So we'll be using GCC for build for the next 100 years before the kernel moves to klang. Okay, thank you. I believe Clang is already used because I believe Clang is supporting all the GCC extensions. Well, we do use it for builds, just like Crest in the kernel. Okay, and the kernel has a mechanism for hot updates. So have you seen how they work? Have you tried to do this rather than reinvent the wheel? Another good question. If you talk about canonical live patch, yeah, most likely. Okay, they have a different approach. They build the objects and they relink the kernel in operation. It's not our approach. When we load our kernel module, we load our product. We don't modify the kernel. The goal is not to patch a critical vulnerability. The goal is to upload a module to patch the kernel and give us more information. That's why the way canonical live patch works. Well, this is a proprietary product. It's not available, and the live patch, the kernel live patch, which is open source, they in README they say you do it at your peril, and it brings together the objects based on the patch. So you download all the source code, you use the patch, you bring the objects, and then you try to fix the running kernel. But it is fixing the kernel, but we are fixing the product. Okay, so you bring together the objects which have the syscalls, then you replace them, and then you unload and patch again. Well, this is, overdoing it. It's much more complicated than this approach. Okay. Two questions. Have you compared your performance with the other hooks and the instruction patching? So you patch the instruction. If at this very time we have a process in the same address performing the same function. Okay, I'll start with the latter question. I didn't mention that the SMP mechanism we use for the CPUs to wait are used for patching the instructions. It works the same way. So we don't see the change of address causing the mismatch of cache. Okay, so you change the 4 bytes. Yes, we change 4 bytes. Well, anyway, I understand what you're driving at. If we change more text, it will be an issue, but we need to jump to some other place. And please remind me of the first question. Well, performance. The hooks, the springboards we have, they don't debuff the performance per se. But the agent doing a lot of work, will impact the performance. The extent? Well, I believe 10%. We are trying to address it so that as many heavy-duty tasks like renumerating hashes should go to some co-workers which are not going to be in between. Hopefully I have answered your question. The performance goes down, but we optimize the kernel to avoid a big drop in performance. Time's up. Let's pick the most interesting question. All the questions have been interesting. Okay. I need to think. I liked this object files question. Can I pick 2 or only 1? Only 1. Okay, then the object files question. Thank you very much for your attention. I'll be there to answer any other questions.